So this week we are moving from electric fields and electric circuits and those type of topics to magnetism. This is the other half of electromagnetism, which is the large majority of what this course is. So when we're looking at magnetism, we're going to start with magnetic fields. We're going to talk about magnetic forces. And then we're going to see some applications. And we're going to see applications on both moving charges and on current carrying wires. So remember that there are two kinds of electrical charge, positive and negative. And as we've seen, likes, charges are going to repel, opposites are going to attract. Magnetism is very similar to that. Sometimes being similar is good, but there are times when magnetic fields and electric fields are really similar and times where they are very different from each other. And sometimes people can learn the magnetic field stuff and get confused when they go back and try electric field stuff. So you have to make sure you really understand electric fields before you look at magnetism. So if you have any questions on that, make sure you contact me so we can talk through some of those. So when we're looking at magnetism, there are still going to be two kinds of magnetic poles, north and south. So the norths, we kind of treat them similar to positive charges. The souths kind of act a little bit like negative charges. So opposite poles are going to attract. So a north attracts a south. And then like poles are going to repel. So north and north repel, south and south repel. If you played around with magnets, they're pretty fun. So if you were to look at them kind of sideways, if you were to try and put the same poles of a pair of magnets together, they'd repel and you would get an attraction if you were to flip one of them around, and so that you get your opposites attracting. So where does magnetism come from? Magnetism actually comes down to an atomic scale and really to some of the things that you learned about in chemistry. So you probably learned that electrons are spinning and that the spins can be either one way or the other. So in chemistry, you represented those spins actually with arrows. So you might have done some sort of atomic orbital type labelings with up and down arrows. So those up and down arrows represent the spins. So for example, looking at this one right here, this one is spinning with the electron in the counterclockwise direction. So what that's doing is that is creating a north pole to a south pole. Our field lines tend to go from north to south when we draw them, but the overall inside of kind of that electron, that's creating this kind of north to south inside, which is what this green arrow here represents. So that would be the same as this upward here in the orbital diagram. And then this one here is spinning the opposite direction. So that one is spinning clockwise, and so that's creating a field in the opposite direction. So you have your up and down arrows. So this is kind of fun because we know that electrons are going to repel each other, and yet these pairs of electrons attract. And it's actually those attraction pairs that are responsible for things like the behavior of noble gases. If all of your electrons are paired, then you're not going to be very reactive. It's the unpaired electrons in materials that make things interesting. And so there's a lot of things that we don't really know. This is just a representation. The electrons aren't necessarily kind of spinning exactly opposite each other. They're not like holding hands. If you have like a chemistry teacher in high school talk about like, oh, they're paired together. They're not even usually in the same location in the atom. They're moving around randomly, but statistically they spend more time together than they do apart. And so this spin creates what we call as a magnetic dipole moment. So dipole means there's two poles, north and south, and a moment means that there is a direction to it. So that is what our spin is creating. So it's these little electrons are these little magnets basically running around with north and south inside of the atom. So if all of your electrons are paired, then your material is going to be non-magnetic. If you have unpaired electrons, this creates a net magnetic field. So this is 1, 2, 3, 4, 5, 6, 7. This is nitrogen. So nitrogen is rarely found by itself. It tends to be paired, N2. And that's because of these unpaired electrons. So those unpaired electrons are creating a net magnetic field. That magnetic field is actually attracting the other nitrogen to it. And well, along with the, with kind of the dipole moments that there are. And so then what ends up happening is if you have another nitrogen, that it kind of rotates and spins or whatever, it adjusts itself so that the pairs get filled. And then your N2 has no unpaired electrons because the 3 unpaired electrons in the one nitrogen atom and the 3 unpaired electrons in the other nitrogen atom attract magnetically and become canceled out. So that's your nitrogen gas is very unreactive. It's in the atmosphere all the time, and it doesn't really do much. Okay, 78% of the atmosphere is nitrogen gas, N2. It's these unpaired electrons that create the net magnetic field. So the more unpaired electrons there are in a material, the stronger the magnetic field is going to be. So the unpaired electrons, these magnetic moments, okay, we are also called domains. And if you're just in a regular material, they're normally random. Think about it. Those electrons are moving around randomly in all directions. If you were to take a snapshot in time, each one of these arrows would represent an unpaired electron or an atom with an unpaired electron, and they're scattered around everywhere. This material would not be magnetic. It's possible to be magnetized, but it is not currently magnetic. It would not attract other magnetic materials. However, if you take a not magnetic material that does have these domains, these magnetic moments, and you apply a magnetic field, we use B for the magnetic field, and it's going to align them. So you can do this to a nail. This is fun at home. If you have a strong magnet, if you just take an iron nail, if you just take an iron nail and you take a magnet, you take the north side of a magnet and you just rub it back and you go in a straight line and you keep going the same way. Don't go back and forth, but you go from left to right, left to right, left to right. You can magnetize that nail. It's kind of a fun little trick. The stronger the magnet you use, the more likely it is that that iron nail will hold its magnetic field. So that's what it means to magnetize a material. Now, the Earth has a magnetic field. So there are some materials that are naturally able to be magnetic. Hematite is one. If you've played with the fun silver kind of polished metal rocks like at a science store or nature stores and stuff like that will have them. Those are naturally magnetic. There are some naturally magnetic materials. That's how we discovered magnetism. So that is the process of which we create a magnetic material and make it magnetized, is by aligning the dipoles. So we apply an external field and then we can turn any piece of iron, for example, or any material that has unpaired electrons into a magnet. So there's a big difference, and that is I can have just a negative charge, an electron. I can have just a positive charge. But isolated north and south poles have never actually been observed in nature. You cannot just have a north side. If you think it, since that electron is what's doing the spinning, and that single electron is creating a north to south, that is already creating 2 poles. That one electron creates 2 poles. So therefore, it'd be really hard to create a magnetic field without having 2 poles at the same time. What's interesting is, of course, with modern science, now we're creating computer models, and there have been in models instances where researchers have been able to create magnetic monopoles in simulations, but they've not been found in nature or naturally, or even through experimentation in a lab, at least not last time I checked. So every time you cut up a magnet, if I have a magnet here, that was originally a north and a south. If I was to cut it in half, all you end up getting is you get 2 magnets. And the reason is this material, remember, is made up of those little dipoles, north, south, So you've got all these little dipoles going in your material. So what happens is you cut this thing in half, you still have your dipoles going the same way. So you are creating another pair of magnets. So now you're creating two magnets. So I have two magnets here. Well, if you were to cut it in half again, you would still get two magnets. So if I were to cut each of these in half, now I have four magnets, each with a north and a south. Now the problem is, in order to get those norths and souths separate, I'd have to be able to cut the electron, but once again, cutting the electron doesn't actually create two separate north and south, so that doesn't really work. So we basically cannot create north and south poles that are separate. So compasses are used to detect and navigate using magnetic fields. So a compass is designed so that it is free to spin. So you can create a really simple compass if you take like a glass of water. You might have done this in like elementary school, and take a piece of cork and just put like a needle on it. And what you do is you magnetize the needle with another magnet. So you do have to have a magnet to magnetize the needle, but then it's free floating on the water and then it can spin. So that's one way to just create a magnet. Of course, a compass, but you have to have a magnet in order to do that. So when you look, the red side of the compass, there's usually a red or a black side, and then the other side is white. The red side of that compass generally tends to point north. So if you look here on this compass, it's pointing north, but it's pointing north because it's attracted to the south pole of the magnet. It's really weird. So the north side of the compass is attracted to the south pole of a magnet because opposites attract. So then why does a compass point north if it's attracted to the south pole of a compass? So compasses are really handy. If we were doing a physical lab, you'd have little tiny button-sized compasses. And you would be given like a bar magnet or a horseshoe magnet, different types of magnets, and you'd be asked to map the magnetic field. And so you can do that by basically looking at where the compass points. So if we were to look at this little tiny compass right here, it's a little different than the one on the previous slide because it's black and red. And if you could zoom in a little better, what you would see is that the north side of the compass here is the black and the south side is the red. So the north side is being attracted to the south side of the magnet. So that's the north side right there being attracted to the south side of the magnet. So how we would do this lab is you would have put the magnet, the compass in place, and you would put a dot like on one end to the other end of where that compass needle is pointing. And then you would move your compass, putting it in the next spot, and you would see that the compass needle is going to start to turn slightly, and it would actually follow the field. And so we'd create a whole bunch of arrows and representing the compass, where the compass is pointing, and we would be able to trace these field lines. It's kind of really cool. Very, very low tech method of being able to map these magnetic fields. Now the direction of the magnetic field at any point is the same as the direction that the north side of the compass would point. So the north side of my compass goes from north to south because it's attracted to the south side of my magnet. And just like with our electric fields, the magnetic field is strongest where the field lines are dense and weakest where the lines are sparse. Now we do have to realize these diagrams do not show every field line. For example, there are other field lines. So for example, I could draw another field line here. Okay. So there would be a field line that kind of goes from north to south. Real magnets are going to have kind of these field lines that kind of come out of the sides. There is actually not going to be, your field is going to be 0 at the midpoint. The compass gets really confused if you put it at the very center of the magnet. And the other thing that's a little bit different is these field lines do actually continue in through the magnets themselves. So if I was to draw a field line, it goes from north to south and then it actually loops back in on itself. So it goes from north to south, and it loops back in on itself. So we can't see the magnetic field inside of the magnet. So on the outside, it looks like the field that's created by a positive charge and a negative charge. But on the inside, these are actually making continuous loops. And all of your field lines are going to be continuous loops inside of your magnets. So we can kind of compare our electric fields and our magnetic fields. So our field created by our magnetic dipole is here. Once again, like these field lines do actually continue inside, so they kind of loop through. And our charges also here would have some field lines, but they would go from positive to negative like that. So that it looks a little bit different inside the magnet as it does for the dipole. So you just have to be kind of careful with that, because your electric fields always start on the positive end on the negative, whereas your magnetic fields make continuous loops. So that's something that's a little bit different. So on the exterior, they're going to look very similar though. Now our magnetic fields here are going to point in the same direction that the north pole of a compass would point. So the magnetic field lines are always tangent to the magnetic field. So if you were to draw the magnetic field at any one point, it's going to be tangent. So if I looked here, my magnetic field vector doesn't curve. My magnetic field vector B is tangent. Okay, it's going to be tangent at any one point. So when I look at any one point, B is actually tangent to the field lines. That's similar with electric fields and the electric field vector. Now, this is kind of weird and funny because when you look at Earth's magnetic field is similar to that of a bar magnet, but there's some differences here. The north side of our compass is attracted to the south magnetic pole. So the north geographic pole is at the North Pole. You know, think Santa Claus right here, right? So Santa Claus is here. Woo! Okay, up here at the north geographic pole. Whereas the south magnetic pole is north. And that's because the north side of the compass is attracted to the south magnetic pole. So Earth's magnetic field is actually upside down. Now the magnetic field does go through reversals. There are actually a lot of research right now that says we're headed towards a reversal. These have happened historically. If you were to look up Earth's magnetic field in geology classes, the seafloor is made of basalt, and basalt has a very high iron nickel content, which are magnetic materials. The core of the Earth is what's creating that magnetic field. And in the seafloor, where the seafloor spreads because magma is coming up through cracks in the mid-Atlantic ridge, what we can see is that throughout history, the alignment of the magnetic dipoles in the basalt flips over very, very, very long periods of time. But if you think about it, birds navigate with magnetic fields. How much of our navigation is based on magnetic fields? There's all sorts of other things that the magnetic fields do for us. What happens if they flip? And so people are worried about, like, what is going to happen if our magnetic field does go through a reversal? So the Earth is not actually a bar magnet. It's not a solid piece of iron in the center. But when you think about the core, what do you think? You got the solid iron nickel core, and then you have the outer mantle, which is also a lot of iron and nickel, but it's molten. That is molten, and so it's moving. So electrons that are spinning, or even just are creating these magnetic fields. So because the molten core of the Earth is moving and rotating, that is what is creating our magnetic field. So if we did not have that molten core, we would not have a strong magnetic field. And the magnetic field protects us from the solar radiation, coronal mass ejections. Sometimes we get big warnings that communications disruptions are going to come because our satellites are going to be affected by the solar wind that's really strong. Our magnetic field protects us from that. Other planets don't have that, and that's can cause a lot more issues, and that's part of the reason why we have life, is we have this nice protective barrier. Now, if you've ever played with iron filings are really fun because they're really small. They move in a line with the magnetic fields, and so you can see that the filings are strongly attracted to the poles where the field is strongest, and they're more spread out and weaker, particularly in the center. If you could look at this at the side, these are also pointing straight up. So the ones here at the poles point straight up because those fields are coming in and out of the page 360 degrees, kind of like your dipole. So here you can see a better diagram of Earth's magnetic field. So it is shaped like the field of a bar magnet. We can see that in the north, geographic north is up here. The magnetic south pole is offset. That's about a 7-degree offset. When that does vary over time as the kind of the rotation of the mantle kind of changes. So if you were to actually follow a compass due north, you will not reach your destination. So if you've ever been orienteering or like on geocaching or anything like that, when you're not using a GPS, you're actually using a compass, you have to be really, really careful, and that there are maps. If you do like really detailed hiking maps for orienteering, they actually tell you what the angle offset is, and the compasses have like a dial that you can rotate to account for the fact that these are actually two different directions. We can see down in our geographic south pole, we have our magnetic north pole. So we do use the symbol B for the magnetic field. The magnetic field lines always go away from the north and towards the south outside. But remember, they loop back around inside from south to north. So inside they go from south to north, outside they go from north to south. The SI unit for a magnetic field is the Tesla. A Tesla is 1 kilogram per coulomb times seconds. The old unit is the Gauss. So you may see problems, or if you do look stuff up on the internet in terms of Gausses, a Gauss is 10 to the negative 4th Teslas. So just a slightly different version. And the reason we would use Gausses is because a Tesla is actually a really huge amount of magnetic field. So in order to do less scientific notation, they used to use Gausses. So Earth's magnetic field has a magnitude of 0.00005 Teslas. So in terms of the amount of Teslas, it's really, really small. There is a better representation here of Earth's magnetic field. You can see it's not perfectly shaped. It does have kind of some different sized lobes based on kind of the wind that the radiation belts. And our stronger magnets, like you might see in use, for example, in your headphones, is about 0.1 Tesla. All headphones work based on magnetism. So there's a little magnet inside of your headphones. And then a powerful electromagnet, like you might have in a research, is about 2.6 Teslas. A superconducting magnet can produce fields over 10 Teslas. If you were ever working in a lab that had superconducting magnets, you would literally, if you were wearing a watch or anything, your hand would get slammed and attracted onto that magnet. 10 Teslas is huge. It would be like some sort of sci-fi comedy movie where someone wasn't paying attention and they get pulled across the room. Maybe not quite that extreme, but it's very, very, very strong if you're wearing any magnetic. So if you're working in a lab like that, you have to take off all your rings and anything that could be magnetic belts before entering the room. And if you're a researcher that maybe had some surgery and had some different types of metal supports put into you, you would not be able to work around those magnets. So when we represent the magnetic field, we use arrows. Now, what you've seen mostly so far is arrows that are pointing left, right, towards the top of the page or to the bottom of the page. Like we had electric field lines like going this way, okay, and that way, and so forth. So that would be like your electric field. When we start working with magnetic fields, we're going to be working much more frequently in 3 dimensions. So left, right, bottom of the page, and the top of the page. Please do not use down or up when you were talking about three-dimensional vectors. Those are very, very confusing directions. Are you talking about up out of the page, or are you talking about up towards the top of the page? So never use up or down. Use top of the page, bottom of the page, right or left. But we also now have out of the page and into the page. So since arrows are how we represent vectors, if you picture an arrow has a tip, and it has the fletching. That's what the little parts of the arrow are there. So if you were to rotate the arrow so that you were looking directly at the tip, what you would see is a point, a dot. So we represent out of the page, the arrow pointing up into your eye, as out of the page. If you were looking at the back side of the arrow, although most arrows have 3 fletchings, not 4, but picture that you're seeing the feathers, the fletching on the arrows, and that is used an X to represent that. So you can see this image right here, we have a field of dots. So this is a magnetic field that is coming out of the page. So picture an arrow coming up into your eye, and then down here, be into the page with all of those X's, that arrow is pointing, those arrows are all pointing into the page. So we have 3 dimensions here, left and right for our X direction. Our Y direction tends to be top of the page, bottom of the page, and our Z direction is out of the page, into the page. Out of the page tends to be positive, into the page tends to be negative, top of the page positive, bottom of the page negative, to the right positive, to the left negative, just on average, okay? Those are the conventions unless they're defined otherwise. So that gives you just kind of a basic introduction to magnetic fields and how we represent them with vectors.